On today's program, the properties of water, the bottling of mineral waters, and a city waterway. The Earth's water is distributed among 5 reservoirs: the oceans, ice and snow deposits, land waters, the atmosphere, and the biosphere. Water journeys endlessly between these 5 reservoirs. Sometimes it adopts a liquid form, sometimes a solid form, and other times the form of a gas. Water covers 3/5 of the Earth's surface. While the planet's most common chemical compound, water has exceptional physico-chemical properties. One such property can be observed when water turns into ice. Most substances, oil for example, decrease in volume and increase in density when changing from liquid to solid. Water, on the other hand, expands when it becomes solid. This is due to the peculiar molecular structure of water. Within each water molecule, the charge distribution creates a positive pole around the hydrogen atoms and a negative pole around the oxygen atoms. Due to the attraction of the oppositely charged poles, bonds form between the water molecules. When ice is formed, the water molecules perform what is known as hydrogen bonding. The resulting arrangement of ice crystals is an almost perfect lattice of considerable volume and of lower density than water. As soon as the temperature of water rises above 0 degrees Celsius, the hydrogen bonds gradually break down, allowing the water molecules to come together again. Water is at its heaviest and densest state when it reaches a temperature of approximately 4 degrees. It's that difference in density between cold water and ice that explains why ice floats in cold water. For the same reason, ice only forms on top of deep water, which happily saves aquatic life in cold regions from being frozen to death. Above 4 degrees Celsius, the density of water gradually decreases. When the temperature reaches 100 degrees, the water molecules break apart and the water becomes a gas or water vapor. Because water vapor is lighter than air, moist air tends to rise toward the upper layers of the atmosphere. The amount of water vapor an air mass can hold depends on the temperature of the air. The warmer the air, the more water vapor it can hold. So when a warm and moist air body cools, such as when moist air rises, the air mass gradually loses its capacity to hold water vapor and eventually reaches a point of saturation. The excess water vapor, which the air can no longer hold, condenses into water droplets. When they become heavy enough, the droplets of water emerge in the form of rain, snow, or hail. Water circulates continually between the Earth, the ocean, and the atmosphere, changing from one state to another. Indeed, the water that falls on the planet as rain eventually evaporates, condenses into clouds, and falls back down to Earth in one form of precipitation or another. Precipitation that reaches the ground follows various courses depending on the regions where it falls. In the polar regions, some of the rain is stored for thousands of years in the form of snow and ice. In milder latitudes, rainwaters percolate into the soil. Part of the water is trapped in small surface pores from where it can be extracted by the roots of plants. Water makes up 80 to 90% of a plant's weight. It enters into the composition of its sap and contributes to turgor, which keeps plants growing upwards. The water absorbed by the roots eventually rises to the leaves, which return it to the air in the form of vapor, in an occurrence known as transpiration. A maple tree, for example, can release over 200 liters of water a day through transpiration. Transpiration produces a displacement of fluid in the plant, stimulating the circulation of its sap. Moreover, it helps to cool the leaves a little in times of intense heat. The water can, however, go deeper into the ground and percolate through several layers until it reaches an impermeable layer of rock. These water-bearing layers are known as groundwater aquifers. The water slowly trickles down to a water bed, feeding any springs it happens to encounter along the way. Any water that cannot filter down into the ground is called surface water. It concentrates in streams, lakes, and rivers. The rivers flow into the seas and oceans, vast expanses of water greatly exposed to the wind and sun, both factors contributing to the process of evaporation. Of the total moisture in the atmosphere, over 80% is evaporation from the oceans. Earth is the water planet, and as far as we know, it is the only planet on which life has developed. This was probably due to water, the source of life. Faced with all kinds of pollution, the notion of pure, plentiful, and inexhaustible water has all but vanished. So much so that people now distrust their tap water. This sad situation has been a blessing for some, as the bottlers of spring, mineral, or sparkling water will tell you. Almost magically, water springs up from the depths of the earth, sometimes salty and gaseous, and sometimes hot. Springs have long been prized for their thirst-quenching and healing powers. There are many different kinds of natural mineral water. Each bears the traces of its underground itinerary and has its own distinct chemical composition and temperature at source. There are cold springs and there are hot springs. A spring is said to be hot or thermal when the temperature of its water exceeds the 20 degrees Celsius point at its source. Salt and gas content also helps to distinguish between the various categories of mineral water. Each category bears the name of its principal constituent. So there are waters that are charged with bicarbonates, sulfated waters, chloride waters, and sulfuretted waters, which have a distinct rotten egg smell. La Salvetat spring water from France, for example, is charged with bicarbonates and is naturally gassy. The origin of most mineral sources still remains uncertain even today. But according to the most logical theory, they come from rainwaters and melting snow, which percolate through the ground. Rainwaters can penetrate very deep into the ground. Some filter thousands of meters down. At such depths, temperature and pressure levels can be very high. These conditions allow the carbon dioxide released by the underlying molten rocks to dissolve in the water. Under the thrust exerted by the carbon dioxide, the water is sent back up to the surface through the faults and cracks in the rock. In passing, it attacks the rocks, dissolving them and becoming charged with the minerals they contain. As a rule, the water cools as it ascends, but if it rises rapidly, it stays hot and comes out of the earth at a high temperature. Once it has reached the surface, mineral water destined to be bottled is handled with great care so as to preserve all its mineral and gas properties. A sample is taken at the source in order to perform a series of quality control tests. The tests performed in a laboratory measure the water's physico-chemical properties and ensure that it is free of bacteria. The water is then degassed. This is done by trickling the water down over baffles in a very high closed tank. The carbon dioxide released during this process is sucked up, liquefied, and stored in a reservoir. Next, the iron in the water is removed because iron affects the water's clearness and gives it a slightly rusty taste. This is done by injecting filtered and sterilized air into the water, which causes the iron to oxidate. The particles of iron oxide can then be extracted by filtering the water through layers of sand. Then a carbonator is used to inject the recovered carbon dioxide back into the water. The water is then stored in a large reservoir. It is only when it is bottled that the water is given back the exact amount of carbon dioxide it had at its source. During the various conditioning phases, the water's physical, chemical, and bacteriological properties continue to be monitored to ensure uniform quality. Then, before each batch of bottles can be shipped out to the market, a final verdict has to come in, that of the water tasters. The water tasters assess the organoleptic properties of the water. That is, all the characteristics that can be perceived by the senses: taste, odor, and appearance. Consumed mainly for their thirst-quenching properties, mineral waters do have their therapeutic uses. Physicians may prescribe a hot spring cure to treat certain illnesses. Back in the 17th century, the famous Marquise de Sévigné used hot spring waters to treat her rheumatism. Vichy water is prescribed to relieve digestive disorders. Thermal cures consist in periodically ingesting small amounts of various spring waters. These cures seem beneficial, but scientists have not yet managed to figure out how they work. Certain minerals in these spring waters are thought to be absorbed via the digestive membrane. Once in the bloodstream, they help to restore its chemical balance. Thermal gases and waters can also be used externally in the form of baths, showers, and massages. These treatments cause the surface blood vessels to dilate, which improves a better overall circulation. The benefits of water to the human body have long been known. The ancient Romans erected imposing buildings to house their hot baths, which in some respects were not unlike our own modern spas.
The worst water pollution is often in cities. However, if we add a few drops of wisdom to our scientific knowledge, even such a threatened ecosystem as a city waterway can be preserved.
Any waterway that runs through a city falls prey to pollution from a surprising source: rainwater. A torrential downpour on a city has the effect of giving it a shower. The rain rinses the buildings and pavement, cleansing them of dust, waste, and all kinds of dirt. Rainwater is charged with micropollutants, such as zinc from the rooftops, cadmium, a metallic element used in car brakes and tires, and lead from the gas cars burn. In addition, the emissions from industry and car engines contain contaminants known as PAHs, or polynuclear aromatic hydrocarbons. Falling rain absorbs any PAHs present in the atmosphere. As it streams along the ground, it picks up any PAHs deposited there. As an example, the rainwaters that fall in a major city, Paris, say, contain about 100 milligrams of dry, polluting matter per liter of water. Once it has cleansed the urban landscape, the rain flows into sewer pipes. As a rule, old cities like Paris have a combined sewerage system. In a combined sewer system, the rainwater runoff is carried in the same drains as domestic wastewater. The drains carry the mixture of surface runoff from rainstorms and sewage to the city's treatment center. When stormwaters are particularly heavy, the drains soon become saturated. They are no longer sufficient to carry the excess flow brought on by the bad weather. To prevent flooding, combined sewers are equipped with safety valves called storm overflows. What happens is that a mixture of wastewater and rainwater is sent, untreated, into the nearest waterway. This effluent therefore discharges all its micropollutants, organic matter, and attendant bacteria into that waterway. Having reached the natural environment, the bacteria begin digesting any biodegradable organic matter. In doing so, they consume a great deal of oxygen, which drastically reduces the amounts the fish need to breathe. When the amount of oxygen available falls to less than 3 milligrams per liter of water, marine life is threatened. To prevent a disaster, scientists have developed a device that pumps oxygen into the waterway when the situation becomes critical. First, bottled liquid oxygen is heated to obtain a gas. The gaseous oxygen is then blown into a network of perforated tubes. The device is let down into the water along the embankments where the distressed fish have sought shelter. The oxygen system ensures the survival of the fish during critical periods. Fortunately, some species are able to adapt and thus to survive pollution. Researchers are currently studying, for example, how one species of fish has adapted to contamination in the river Seine, which runs through Paris. They are comparing one school of roach that inhabit the Seine upstream of Paris to another living downstream. First, the researchers capture a few fish from each school by inducing an electrical field in the water. The fish subjected to the field are drawn to a positive pole, where a researcher catches them in a landing net. The fish are then measured, weighed, and studied before being returned to their natural habitat. The studies have shown that the fish that live upstream of Paris, hence less exposed to the pollution, have a longer lifespan than their downstream counterparts. Because of their shorter life expectancy, however, to ensure the survival of their species, the roach inhabiting the Seine downstream of Paris have developed a number of adaptations. They reach full maturity earlier, for one, and their fertility, that is, their ability to reproduce, is greatly heightened. Humans are also trying to find ways to curb pollution, among others by reducing the amount of wastewater being discharged into the environment. Some cities, for instance, have installed tanks to collect the excess stormwater their sewer systems are unable to handle. Another strategy involves the installation of reservoir pavement in parking lots, certain traffic lanes, and on sidewalks and driveways. This particular type of pavement is porous, which allows rainwaters to seep through. The reservoir structure is installed beneath the pavement. Made of crushed stone, it is used to store any excess storm water. The water can later be drained off at a rate the system can handle. So while human resourcefulness works to curb pollution and lessen its effects, our fellow living creatures adapt to better overcome it.
In the old days, sullying water was considered a crime and was severely punished. Nowadays, unfortunately, the wrath of the gods has turned into political rhetoric.